Hello. Now we're going to continue talking about trigonometric functions of angles considered as rotations. And we're going to start to touch on this concept of a reference triangle. Okay, so you can see we have an angle rotation here. We have a positive angle rotation rising up in the counterclockwise direction off my positive x-axis. And we have a terminal side. So let's list some points here. So this terminal side, we have some point right here. We'll call it point P, which is an XY ordered pair. And point P lies on the terminal side. So we can think about this, and we'll call this guy here R, a radius. What you want to notice is there has been a vertical line dropped down. Okay, so from that point on the terminal side at a specific or specified radius extended out on that terminal side, we're going to drop a vertical line. And this is going to let us create a reference triangle. So we're dropping a vertical line. It is always going to be up or down. So you are never going to draw a horizontal line. When you're creating a reference triangle, you're always going to be going up or down to the x-axis. Okay, so we're dropping a vertical line always up or down, and it's always going to the x-axis. We have to do it in the same way so that when we specify our rules, that we can always use the rules because it will make sense within the way we have defined it. Okay, so we've dropped that vertical line down, and it's vertical, so we're going to call that y. And then we have a horizontal distance here, x. So if we travel out x and up y, that takes us to our point xy. And so then this hypotenuse of this right reference triangle that we've created, that's always going to be what we call our radius. So just to re-specify, we always create a reference triangle by drawing a vertical line down or up to the x-axis. So you can see in each of these three other quadrants, quadrant 2, quadrant 3, and quadrant 4, our reference triangle is in relation to the x-axis. Never draw the horizontal line. So something we want to notice, considering this picture that we have here, the opposite side is always vertical, right? There's my y, and that is always opposite that small angle. And the adjacent side is always going to be horizontal. And then my radius is always the hypotenuse. So if we draw that line vertically up or down to the x-axis, our sides are always going to be oriented in the same way. So the reason this is useful and the reason we like this is because this means that our reference triangle is always going to have this same pattern. You're going to have some acute angle theta, which is in near the origin. You're going to have a horizontal side x, which is adjacent to theta, a vertical side y, which is opposite theta, and we'll have r, or our hypotenuse. So we can define these. I can say, well, sine theta, remember SOHCAHTOA. SOHCAHTOA lets us know that sine's opposite over hypotenuse. In this case, that is y over r. Cosine theta is adjacent over hypotenuse, so that would be x over r. Tangent is opposite over adjacent, or rather, sine over cosine. So then we know that tangent theta is y over x. And if I were to take sine and cosine and put them over each other, see, I would get y over x. So we want to remember these, and these are really the exact same, three definitions we specified previously in this section. It's just we've written them differently. Sine is still opposite over hypotenuse. Cosine is adjacent to theta over the hypotenuse, and tangent is opposite theta over adjacent theta. We also know that these reciprocal definitions are going to operate in the same manner. So what is reciprocal to sine? And that's cosecant theta. So cosecant theta is r over y. What is reciprocal to cosine? We have secant theta. That would be r over x. And reciprocal to tangent is cotangent theta, x over y. So again, we have these new definitions, but they're really just the same definitions we already had. We're just using different variables. All right. So since we know the signs of x and y in each quadrant, we know the sign of all of the trig functions in each quadrant. So we're building towards this unit circle logic, right? We don't know what the unit circle is, but I'm kind of giving you all of these clues so that it will all tie together here in a couple of videos from now. So one thing that we keep in mind is both x and y are going to be positive in quadrant 1. X is negative, y is positive in quadrant 2. Both x and y are negative in quadrant 3, and x is positive and y is negative in quadrant 4. Ugh. All right, so why are we starting to think about these sines and cosines as x's and y's? Well, sine is y, cosine is x, tangent is y over x. You say, well, we have this r in here. R is always going to be this positive extension. It'll be a positive value extending out. So dividing by a positive isn't going to change the sign of anything. So moving forward, we're going to start to connect that cosine is going to be some x value and sine is going to be a y value. So both cosine and sine are positive in quadrant 1. And tangent, which would be sine over cosine, positive over positive, will also be positive. All right, so sine is going to be positive. My y value is positive for sine, and cosine is negative. And if I did a ratio of these, I would get a negative number for tangent. Quadrant 3, both are negative. Sine is negative, cosine is negative, and a ratio, negative over a negative, that's going to give me a positive tangent. And lastly, we have a positive cosine and a negative sine. So cosine's positive, sine is negative, and a ratio, negative over positive, tangent would also be negative. Thinking about these 4 quadrants, we got quadrant 1, quadrant 2, 3, and 4. We are going to remember A, S, T, C. All S, T, C. All students take calculus. So this is my mnemonic device that I use here. So all my trig functions are going to be positive if I'm dealing in quadrant 1. Sine is the only trig function that will be positive in quadrant 2. Reciprocal to sine, we also know we would have cosecant. Tangent and cotangent would be positive in quadrant 3. Cosine and secant would be positive in quadrant 4. All sine, tangent, cosine, or all students take calculus. So moving forward, as I am working problems, I'm going to think to myself, A, S, T, C. All right, so I hope that makes a little bit of sense to you. So again, right now, we're learning all these little bits and pieces so that we can pull them together and synthesize them to use for our unit circle logic. So here we have a problem. If the terminal side of an angle falls on the x or y axis, it is called a quadrantal angle. And so those xy coordinates are always going to end up being a combination of 0 or -1. So as we build towards this unit circle logic, we're always going to be thinking about this circle. And the smallest, easiest to deal with radius circle I can come up with is a circle of radius 1. If I have a circle of radius 1, and we think about these 4 points that would be on these quadrant edges, we'd have 0 degrees, 90 degrees, 180 degrees, 270, back to 360, which is coterminal with 0. So if this is a circle of radius 1 and I wanted to list all these ordered pairs, this first dot we would have 1, 0. Up at 90 degrees, we would have 0, 1. At 180 degrees, we'd have -1, 0. And at 270, we'd have 0, -1. So using this sine and cosine logic, we said that cosine theta is going to be our x, and sine theta is going to be our y. What would be sine of 180 degrees? 180 degrees takes us over there. My y value, because sine is y, my y value is 0. Sine of 180 degrees is 0. Or you could think about it as being y over r. Well, that is 0 over, this is a circle of radius 1, which is just 0. Tangent of 270. So we rotate around, we come to 270 down here at the bottom. What we want to remember is that tangent is that ratio sine over cosine, or y over x. My y value is -1. My x value is 0. I can't divide by 0, so my answer here is undefined. So I got 2 answers, 0 and undefined. Let's do one further example. We're going to find these 6 trig values created by the point -2, -3. And remember, we're still going to be thinking about this using the fact that sine theta is y over r, cosine theta is x over r, and tangent theta is that ratio y over x, sine over cosine. So let's sketch this. The point -2, -3 is in quadrant 3. We have a point roughly here. So we have some angle created by that point. It's a full rotation around this way. That would be the positive angle rotation. This angle is greater than 180 degrees, and that's kind of hard for us to visualize because so far almost every angle we've dealt with has been inside a triangle, and triangles can't have angles more than 180 degrees. So this is my angle rotation, theta. So what we want to think about, though, is creating a reference triangle. When we create a reference triangle, we're always going to drop a vertical or raise a vertical up to the x-axis. So doing so, now I have this small triangle here. So we have some smaller angle, maybe we'll call that alpha, occurring in here. Now I know the measurement of my x and y values. The length of my x side is -2. The length of my y side, I'll draw that in blue, -2. The length of my y side is -3. Can I find the length of my radius? Yes, I can find that length using the Pythagorean theorem. So by the Pythagorean theorem, we would say -2 squared plus -3 squared equals r squared. 4 plus 9 equals r squared. We're going to end up with r equals plus or minus the square root of 13. Now, as I already said, that radius is going to be positive. It's always extending out. So that's going to be positive root 13. All right, so now that we have these three sides, we can state all of these 6 trig function values. So I'll come so far as to say, well, sine of theta is y over r, -3 over that radius, positive root 13. Cosine theta is x over r, -2 over root 13. And tangent theta is sine over cosine, or my y value, -3, over my x value, -2. So I'm going to simplify these, but before I simplify them, I'm going to go ahead and write my reciprocal function values. So cosecant theta is negative root 13 over 3. Secant theta is negative root 13 over 2. Cotangent theta is 2 over 3. So simplifying that, I've got sine theta. If I rationalize that, I've got -3 root 13 over 13. Rationalize -2 over root 13, I have cosine theta is -2 root 13 over 13, and tangent theta, just the negative over negative, becomes positive 3/2. So these are my 6 trigonometric function values created by that point located at -2, 3. I have a question. What quadrant is -2, 3 in? We're in quadrant 3. And if we go and we think all students take calculus, we have a t in quadrant 3. That means tangent is the only trig function positive in quadrant 3. tangent's positive, and its reciprocal, cotangent, are positive. All of these four, sine, cosine, secant, and cosecant, those are all negative. All right, so I'm going to stop this video for here, and then we'll finish working on this in the following video.